Hello everyone. As we all know, the basics of mathematics is a set. In a set, if we define an operation and the set together with the operation will be the basis for algebra. And in a set, if we define a function, then the set together with the function will be the basis for analysis. Here we are going to see some basic concepts in real analysis. First, we are going to see the definition of a metric space. A metric space is a function D. Usually it is known as the distance function. That's why we are using the symbol D. D on a set M, and the function D is from M cross M to R such that it will satisfy the four conditions for all elements of X and Y in M. First condition is non-negativity. That is, the distance between any two points should be greater than or equal to 0. Second condition is d of x comma y equal to 0, that if and only if x equal to y. That is, the distance between any two points is equal to 0 only if the two points are equal. Third one is the symmetric condition. That is, the distance between x and y and the distance between y and x should be the same. Fourth one is triangular inequality. D of x comma y is less than or equal to d of x comma z plus d of z comma x. These four conditions should be satisfied for all the points in M. Next, discrete metric space. In a metric space, if we define in a set, if we define the distance function d of x comma y is equal to 1 if x not equal to y and 0 if x equal to y. That is, if the two points are not equal, then the distance measurement will be equal to 1, and if the two points are equal, then the distance measurement will be equal to 0. If we define the metric as like this for any set M, then this metric is known as the discrete metric on the corresponding set M. Next, we are going to see some examples. In the real line, discrete metrics can be defined for any set. Here in real line, we are going to see some more metrics that can be defined. First one is, if we define the distance as d of x comma y equal to modulus x minus 1, then this d also satisfies the requirement of a metric space. This d also serves as a metric, and this metric is known as a usual metric on R. Next, in real line, if we define d of x comma y is equal to x minus y the whole square, then if we check the conditions for the metric, this definition will not hold for the triangular inequality. For that, we can give some numbers and check. Here we checked using the numbers x equal to 3, y equal to 1, z equal to 2. This will not satisfy the triangular inequality for this particular function. Therefore, d of x comma y equal to x minus y the whole square cannot be a metric on R. Next example is the generalized case of the usual metric on R. In R power n, the usual metric is defined as d of x comma y equal to summation taken over I equal to 1 to n xi minus yi the whole square the whole power 1 by 2. Where x equal to ordered n tuples x1, x2, etc. up to xn, and y equal to ordered n tuples y1, y2, y, etc. up to yn. And this metric is known as the n-dimensional Euclidean space metric. We can also see some other metrics on R power n. Here I give some examples. D of x comma y equal to summation I equal to 1 to n xi minus y the whole power p whole power 1 by p. This also serves as a metric on R power n. d of x comma y equal to summation I equal to 1 to n modulus xi minus yi. This also serves as a metric. D of x comma y equal to maximum of modulus xi minus yi. I varies over 1 to n. Also, d of x comma y equal to summation I equal to 1 to n ci into modulus of xi minus yi, where that ci is of fixed positive real numbers. Next we are going to see some important concept, that is bounded sets in a metric space. Definition. A subset S of a metric space is bounded if there exists k greater than 0 such that for all x and y in S we have d of x comma y less than k. In sequences, the boundedness is corresponds to the set. If the set is bounded, then we can say the sequence is bounded. But here the boundedness is corresponds to the metric. Here for a set we have to measure all the distance between any two points. For that distance, if there is any bound, or else if the distances are bounded by any particular value, then we can say the corresponding metric space is a bounded set. These are the examples of a bounded set. As usual, any finite subset of a metric space is bounded, since here we are going to measure distance between particular points in the finite set. Therefore, we can fix the boundary here. Next, any finite interval or a set which is contained in a finite interval is bounded in R. Next example, 0 comma infinity, open interval 0 comma infinity, or it is closed interval 0 comma infinity. Both are unbounded subsets of R. Next, in the previous example, we gave some metrics on R power n. In the matrix, the fourth example will be a bounded set. Thank you.